several roomfuls of salt.
Indeed, indeed.
Because they're speculating, they just want the stock price to go up. Anyway, we should probably.
Yeah. So let's go on to this. I think my plan was to actually talk about this idea of the of a project, of an optional project up front, and to then go into the material. But I think, given late arrivals, we'll go to the material first and then talk about the project later. Which is not so bad, because I don't think we'll spend the entire time on this. So I'm going to be talking today about one of the several types of networks we talked about last time. So who can remember some of the types of networks other than scale-free networks we discussed in the last session?
The ring networks?
Ring networks, yeah. So ring lattice, they're commonly called. You're connected purely locally in a what sort of configuration? Essentially a 1D. It's like a long execute joined at the other side. There's this, I don't know if you folks are familiar with it, if you would have encountered it in previous classes, but it's actually a really useful notion, notion of a manifold. Have you folks encountered a manifold before?
Heard of it.
Yeah. And without wanting to go into it and define it formally in a mathematical sense, has to do with differential geometry. The notion is you could be in a, say, a 2D space, but have a structure that's essentially 1D within that space. So, for example, you could have, a line in 2D, but more interestingly, you could have a ring in 2D. Yes, a ring in 2D. This is essentially a locally 1D structure. One-dimensionally, at any point, it looks one-dimensional. And one way one could develop confidence about that is if you started at a point and you went out from that point, and you were to count the other number of points sort of as you go out, it would rise linearly as with the radius as you go out from this point locally. In other words, you start at a point in this ring, you go out for a long time, all you're going to see is number of points that rises linearly with the radius. And that's a sign that locally it's a 1D structure. Now globally, it has some 2D elements. I mean, it connects together at the end, but this is essentially a 1D manifold in 2D space. One of the reasons this comes of use is if you start looking at some of the state spaces of the models. Suppose you have an SIR model where there's no deaths. It's a closed population. No births, no deaths. It's a fixed population. You can represent this in a 3D space. So S, I, and R. You can represent this in a 3D state space. Right? So you could create a state space which is three-dimensional. One dimension will be what? Give me one dimension of the state space. S, thank you. I, and it'd be R. So if those two were going that way, this would be going this way. So we have this sort of three-dimensional state space. But if this is a closed population, the R is just given by n minus s minus I. Right? There's a conservation of people. They're in one of those states. And so actually, this is going to occupy a two-dimensional manifold within 3D space. In other words, it might occupy, for example, a plane, or it might occupy a sort of curved plane within this space that locally is 2D, but it's embedded in a 3D space. Okay, so we could describe this in a 3D state space to be sure, but because of the conservation properties involved, it actually only occupies 2D out of that state space. Okay? This is of considerable interest when it comes to dynamic modeling, because we're often simulating systems that are not only highly complex with lots of moving parts and lots of different elements of their state space, but they're highly coupled. In other words, the different parties within the system are interacting. And if you think about an agent-based model, compared, here we have SIR model, an aggregate model, we have a three-dimensional state space, although we may only occupy a two-dimensional subset of it. In an agent-based model, what's the size of our state space? what's the size of the nominal state space? Sort of you know, if you map things out, you weren't thinking about what's the true occupied form, what's the size of the nominal state space? Well, let's suppose each agent could be one of three states, susceptible, infected, recovered, in an agent-based model. So here we have our agent-based model, here we have our agents, here, and each agent can be in either S, I, or R state. And suppose we have N agents. Yeah, it's 3 to the N. In theory, we could have 3 to the, by convention, capital N. For each agent, they can be in any of 3 states, right? And another agent can be in any 3 states, etc. And so we have a combinatorial explosion in the number of states that the whole system could be in, right? In theory, everyone but this person could be infected. Everyone but this person could be recovered. You know, only this person could be infected. The rest could be susceptible. What happened? Now, so that much is true. We have a nominal state space of that dimension. Now, if you were to instead ask what is the underlying intrinsic dimensionality, the actually occupied dimensionality of the state space, it actually may be much thinner than that, in the sense that certain configurations here are infinitesimally unlikely to occur. Certain configurations are impossible. One example would be maybe these 3 are connected. Maybe this is a distance-based network. These 3 are connected together, and this other one is disconnected. And if you start it in a fully susceptible state, this guy is never going to get affected. So you can rule that out as an element of state space. But more generally, the evolution of the system is going to go through a set of configurations which are actually going to be quite low dimensional. A system, even though in theory, this system, if we have a simple SIR type model here where people send to their neighbors or what have you, really we're going to be proceeding in simulating the system in a fairly low dimensional way. That is, there's only a small subset of that space, as I said, a manifold, a sort of lower dimensional subspace that's actually in fact going to be occupied. And it won't be anything too different than this. Here we have 3 dimensions, we're actually only occupying 2. Here we might have 3 to the n dimensions, thousands, millions, billions of dimensions, but we're actually only occupying effectively a very small sliver of that. Now, because of the stochastics involved, it's not going to stick just to this. There's going to be some stochastics around it and so on. But we're going to be occupying a very, very thin component of it. So I've done some experiments with agent-based models and looking at the dynamics. And what you actually do find is predominance of, say, 2-dimensional dynamics or 3-dimensional dynamics in a model that's otherwise quite sophisticated. You have agent mobility, moving around, transmitting infection from one agent to the other. And you might actually have an intrinsic dimensionality that's 2, 3, 4 dimensions, something like that, as judged by this criteria here. You look at a radius, you look at how many points are included in a radius. This idea takes advantage of the fact that, you know, if we have a 1D thing, you know, the number of points rises with R. If we have 2D, it rises with R squared. If we have a sphere, the volume rises with R cubed. And so here, we can use this sort of relationship, this reflection, to judge the intrinsic dimensionality of an object. There's a thing called Fox-Cunning dimension, a Hausdorff dimension, and there's other names for ways of measuring intrinsic dimensionality. So what we're seeing with our agent-based models is models that are incredibly big in terms of their state space, almost intractably large state spaces to enumerate. But in terms of the actual exercise degrees of freedom, in terms of how much of that state space they actually occupy in their movements, it's actually quite small. It's quite limited amounts of the state space. Just as in this case with the SIR model, we only occupied a manifold of dimension 2 out of 3 dimensions. And that was because we had a conservation of people, s plus I plus r equals n. So we actually only occupy a 2-dimensional subspace of this. Now, it could be curved. It needs to be a strict plane or something like that. But locally, it's 2-dimensional. Okay. In this case, it actually is a plane, but it needn't always be. So here we can have this high-dimensional space. Now, the interesting thing is, often you end up occupying a much lower dimension if you have a couple things. One thing is conservation, like this case. Another thing is symmetry. Another thing would be high coupling between components. We've looked at, for example, intrinsic dimensionality associated with human behavior, using a whole bunch of different sensors tied together, your location, how many people surround you, your level of physical activity, et cetera. And if you start enumerating out these things, you might think there's a huge state space, but in fact, these things are highly coupled. I rarely do high levels of physical activity when I'm in the washroom or something like that. In other words, the context I'm in will often dictate several of these things together. Things go together in terms of my behavior. When I'm in certain places geographically, I behave in certain ways. When I'm in this room, I tend to behave in certain ways. When I'm in the context of a bus station surrounded by people, I will often behave in a certain characteristic set of ways. So in short, the intrinsic dimensionality associated with human behavior is a lot smaller than you might think. And in fact, if you start considering multiple people, just like you do here in multiple agents in an agent-based model, we start considering multiple people. Actually, there's huge correlations between their behavior. We come together as a group for this class, and our behaviors are coupled. Alex, your same with the 371 team's behavior is coupled. Perhaps less so than you might. You know, in terms of coordination, less so. But people go to work at roughly the same time. They go home. So in short, if you know my location at a certain point, it tells you quite a bit about your locations at that point. If you know I'm here teaching, it's a good chance that people in the class will be here. But it's not guaranteed. So in short, this coupling between different individuals actually leads to occupying a much smaller subspace than you might otherwise expect within state space. So these models, within state space, they evolve. We'll have a state space that's drawn out. Maybe it's 3 dimensions, maybe it's 3dn dimensions. But we will evolve within that state space over time. A given run of the model might do something like this. Maybe it's cyclic or what have you. But that trajectory may be on a much lower dimensional manifold than the nominal value of the dimensionality of the space. It may be on the intrinsic dimensionality of the actual behavior that's possible may be much, much, much smaller. And this is, interesting fact. It's also a challenge. It raises the possibility, if you're only occupying a sub-area of the space, it suggests that you might be able to create a simpler model. A model that can account for it with fewer state variables, for example, which is an intriguing possibility. So anyway, those are some comments on state space. The reason I started to talk about that was there's an underlying linkage with some of the ideas we talked about today with networks. But having done that recording, I think I'm going to actually